Good morning. We're going to continue on with our unit on limits and continuity and talk specifically about continuity in this section. First things first, what does something that is continuous mean to you? Well, that might mean having no breaks or interruptions. In calculus, continuity is used to describe functions whose graphs have no breaks. So if you look at this first graph on the left, there's not a break in the graph. On the right, however, there's a break right here at C. That's called a discontinuity. For continuity at a point, you're going to assume that f of x is defined on an open interval containing C. We will say that f is continuous at that point, x equals C, if the limit is equal to the value of the point. If the limit doesn't exist, or if it exists and is not equal to f of C, then it has a discontinuity, or it's discontinuous at C. So it's possible for functions to be continuous at some points and not at others. If f is continuous at all points on an interval, then it's said to be continuous on the interval. There's some information here as far as left endpoint and right endpoint. So for the first example, we are going to show that a limit is continuous. And we learned already that the limit of a constant, which is k, as x approaches any number, is going to be k. If I plug a value in, I should also go and get k. So we can say that f of x is continuous because limit of f as x approaches c of f of x equals f of c, which is going to be the k. Okay, so this is very important to be thorough. In geometry, you learned how to be specific about your steps. That applies here because in AP Calc, if you don't qualify something as continuous, then you can't use some of your theorems. For the next one, we need to show that the limit as x approaches c of g of x equals that number to a power. We need to show that g of c is also going to equal that number to a power. And I'm going to write this a little differently. Since g of, let me rewrite that. I'm going to write that differently. Limit as x approaches c of g of x equals g of c, which is equal to c to the n. So this is your statement. This is our conclusion. And those three dots mean therefore g of x is continuous. And you can abbreviate in AP. Okay, requirements to be continuous. F of c is defined, the limit exists, and they are equal. So that's exactly what we just showed. There are two types of discontinuities. Removable means the limit exists, but it's not equal to the point, and we could just plug in a point to make it continuous. And a jump discontinuity means the one-sided limit exists, limits exist, but they're not equal. Okay, so here's your removable discontinuity. If I were to plug this point in here, it would make it continuous, so it's a removable one. And then your jump discontinuities, there's actually a jump in the graph. Okay, so we are going to discuss discontinuities of functions. Okay, so I'm going to look at each value, 1 and 3. I'm going to look at the limit as x approaches 1 from the left of f of x, should make that a capital, and the limit as x approaches 1 from the right of f of x. Now, if I'm going from the left, that means x is less than 1, so I have to use this here. So what I'm going to do is just plug the number in. I get 1 there. If it's coming from the right, we're looking at this one, because that's where the numbers that are bigger than 1 are going to be. And since this is a constant, our limit is 3. So we know the left-handed limit is 1, the right-handed limit is 3, That means there's a jump discontinuity at x equals 1. We're going to do the same thing for 3. So the limit as x approaches 3 from the left of the function, and the limit as x approaches 3 from the right of the function. So on the left, this is constant, so that's going to be 3. Okay, so coming from the numbers that are smaller than 3. The numbers that are bigger than 3, we're just going to plug that in. So plug in 3 for x, and we get 3. Now, since those two are the same, and if I found f of 3, okay, so when x is equal to 3 here, we're going to use 3. Since those two are equal and f of 3 is equal to that limit, this is continuous at x equals 3. Okay, so both limits are equal, the point is defined, and it is also equal. We're good. Okay, so go back to these requirements. F of c is defined, the limit, both one-sided limits are the same, and then they're equal. Okay, there are also infinite discontinuities, and that is when one or both of the sides is infinite, even if it's not defined. So you're going to look here, you'll notice that for the most part, we have vertical asymptotes. This last one is the only one that doesn't. Okay, so building continuous functions. How can we show that a function is continuous? We have laws of continuity. A function is continuous if it is built out of functions that are known to be continuous. So there are basic laws of continuity for you to use as reference there. And here, continuity of polynomial and rational functions, continuity of some basic functions, and continuity of composite functions. There is a note here that elementary function is a function that is constructed out of basic functions using the operations of addition, subtraction, multiplication, division, and composition. Since basic functions are continuous on their domains, an elementary function is also continuous by the laws of continuity. These are in your book. I'll have you refer to those and copy those down so you have them. Okay. Substitution method, I kind of talked about this before. When the function in question is known to be continuous, you can evaluate a limit by plugging in x equals c. So we know that sine is continuous. So to find the limit, we're going to do sine of pi over 3. Now I know it's been a while, but pi over 3 on the unit circle has the short side here, long side here, so it's 1/2 square root of 3 over 2. And we're looking at our y value, so our limit is going to be the square root of 3 over 2. Just plug it in. Okay, I know that 3 to a power is continuous. I know that the square root of x plus 5 is continuous, so I can substitute those in, 3 to the negative 1, and then the square root of negative 1 plus 5, and I can simplify to get square root of 4 is 2. If I rewrite this, I get 1 over 3 times 2, so my limit is 1/6. The last thing I want to talk about is a greatest integer function, and I can pull that up on a graph here in a second. But the greatest integer function is defined by a step value of x equals n, where n is the unique integer such that n is going to be less than the value, less than or equal to the value, which is less than n plus 1. So what you're doing essentially is taking that decimal and dropping it off. Okay, so if I have 4.7, that's the same as saying 4. If I have 4.1, that's also the same as saying 4. So when I look at this problem, because there's a jump in the graph, my answer is that we cannot use substitution because the function is not continuous. And I'm going to put this graph up here so you can see what the graph looks like. Okay, so when I say 1.5 is going to be 1, if I take 1.5 for my x and plug it in, I end up having 1 consistently. So at 2, you'll notice there's a jump discontinuity there. Okay, so we can't use that method. And that's it. So lots of practice. Do your best. Let me know if you need help. Have a great day.